Beneath our cities, across continents, and under the vast oceans, lies a silent, invisible network. Millions of miles of glass threads, relics of the 1990s internet gold rush, laid down but never used. This is dark fiber, and it's being awakened for a purpose its creators never imagined. We're turning this forgotten skeleton of the internet into a planetary-scale nervous system, capable of listening to the very heartbeat of the Earth. Welcome to Geophysics Online, where today we're exploring how these dormant cables are becoming the world's most powerful earthquake detector. This isn't just an upgrade for seismology. It's a revolution that's turning our global communications grid into a colossal scientific instrument. At the heart of this transformation is a technology called Distributed Acoustic Sensing, or DAS. Imagine a fiber-optic cable, a glass thread thinner than a human hair. A special device called an interrogator unit, connected to one end of this fiber, acts like a super-powered radar gun. It sends thousands of short laser pulses down the glass every single second. Now, even the purest glass fiber isn't perfectly uniform. It has microscopic imperfections, natural flaws from the manufacturing process. These tiny flaws are scattered all along the cable, and as the laser pulse travels, each flaw reflects a minuscule amount of light back to the interrogator. This constant stream of reflected light is called Rayleigh scattering, and it creates a stable, unique fingerprint for every single section of the fiber. Now for the magic part. When a seismic wave from an earthquake travels through the ground, it causes the Earth, and the cable buried within it, to stretch and compress by an almost imperceptible amount. This tiny movement changes the distance between those microscopic imperfections in the glass. That change, as small as it is, alters the travel time and the phase of the light being scattered back to the interrogator. The interrogator uses a technique called interferometry to detect these subtle shifts in the returning light. By precisely measuring the timing and nature of these changes, the system can pinpoint the exact location and intensity of the vibration along the entire length of the cable. What this means is that every few meters of a fiber-optic cable effectively becomes its own individual seismic sensor. A single 20-kilometer cable, something that might run across a small city, can be transformed into an array of 10,000 motion sensors. This is the core idea of dark fiber geophysics, turning existing infrastructure into a high-resolution seismic array on a scale we've never seen before. Interestingly, this technology didn't start with earthquakes. It actually has its roots in the oil and gas industry of the early 1990s. Companies first used fiber optics to get single-point temperature and pressure readings from deep inside oil wells. This evolved into distributed sensing, where the entire fiber could monitor conditions like fluid flow and the effects of hydraulic fracturing. It was a logical, yet brilliant leap for seismologists to look at this technology and see its potential for studying the Earth itself. They realized that the millions of miles of dark fiber laid during the 90s tech boom represented a pre-installed global sensor network just waiting to be turned on. Pioneering work by scientists at places like Berkeley Lab, Caltech, and Stanford University began to prove the concept. Early experiments around 2017 involved burying their own cables and comparing the DAS recordings with traditional seismometers placed right next to them. The results were clear. DAS could detect everything from quarry blasts to local earthquakes, and the data matched up beautifully with conventional instruments. A huge breakthrough came when a team at Stanford used a 3-mile loop of regular, pre-existing telecom fiber running through conduits on campus. A key question was whether these cables, just sitting loosely in plastic pipes and not perfectly bonded to the ground, would be sensitive enough. The answer was a resounding yes. The array detected hundreds of events, from tiny local tremors to massive earthquakes thousands of miles away, proving that even this loose coupling was good enough for high-quality science. This is where the true power of dark fiber really outshines traditional methods. For over a century, earthquake monitoring has relied on a sparse network of seismometers. Even in a place like California, these stations might be several kilometers apart. With DAS, you get a sensor every few meters. It's the difference between looking at a grainy, pixelated image and watching a high-definition video. This incredible spatial resolution lets scientists see the fine-scale details of how an earthquake rupture unfolds and how the ground shakes in different areas, details that are completely invisible to conventional networks. Then there's the cost. A single research-grade seismometer can cost up to $50,000 to install and maintain. With dark fiber, the cable is already there and paid for. The main investment is the interrogator unit, making high-density seismic monitoring economically feasible on a massive scale for the very first time. This also allows us to expand into uncharted territories. About 70% of our planet is covered by water, and it's a massive blind spot for seismic monitoring. Destructive tsunamis are often generated by offshore earthquakes we can't see well. But thousands of submarine telecommunication cables crisscross the ocean floors. Tapping into these undersea cables means we can create dense offshore seismic arrays, revolutionizing our ability to detect submarine quakes and improve tsunami early warning systems. The same goes for dense urban centers, where digging up streets to install traditional sensors is often impossible. We can just plug into the fiber network that's already there. The real-world results are already pouring in, and they are spectacular. After the powerful magnitude 7.1 Ridgecrest earthquake in California in 2019, scientists quickly connected an interrogator to a dark fiber cable running through the area. For over 80 days, this ad hoc array recorded thousands of aftershocks, many of which were too small to be picked up by the regional seismic network. The data revealed something incredible. Ground shaking could be dramatically different from one city block to the next, amplified by local soil conditions. This kind of fine-scale hazard mapping is a game-changer for improving building codes and urban planning. The Stanford University campus loop I mentioned earlier became a permanent urban seismic observatory. Despite the noise of a busy campus, it recorded over 800 events in its first year and clearly distinguished between the arrival of the initial P waves and the more destructive S waves. This is a critical capability for any earthquake early warning system. In Japan, researchers connected a DIS unit to a spare fiber in a 105-kilometer-long seafloor cable off the coast of Sanriku, a region prone to massive quakes. The system created a dense offshore array and successfully recorded numerous earthquakes, from tiny local tremors to large distant events. This is a crucial proof of concept for monitoring the world's most dangerous subduction zones. Perhaps most exciting is how DAS is changing our fundamental understanding of earthquakes. In one study of a magnitude 6 quake, the high-resolution fiber data revealed that the main event wasn't a single rupture. It was actually a sequence of 4 smaller, distinct sub-events that happened in quick succession. These mini-quakes were completely imperceptible to standard seismic networks, but gave a much more detailed picture of how the fault actually failed. We're literally seeing earthquakes in a new light. Of course, this revolutionary technology isn't without its challenges. One major issue is the signal-to-noise ratio. Because the fibers are so sensitive, they pick up everything, not just earthquakes. In cities, this means a constant hum of